Hey, VSauce, Andrew here. I'm just going for a ride and phew, that was a lot of work. Work is a change in energy. But what is energy?
Energy is defined in physics as the capacity for doing work. Energy can exist in many forms, which include thermal, nuclear, chemical, electrical, etc. It also cannot be lost or created. It is always conserved. This is called the law of conservation of energy. So, how can one type of energy be lost or created? It can't. Energy can be converted into other forms of energy, meaning that chemical can become nuclear, which can become thermal, and so on. But the total amount of energy in the universe is always the same. Now, let's take a look at this principle in action, and to do so, we'll take a look at another form of energy, mechanical. One type of mechanical energy is kinetic, the energy of motion. Now, right now, this block is not moving, even after I politely asked it to. But when I drop the block, it has kinetic energy from the moment it leaves my hand, increasing in magnitude until the moment it hits the surface of the table. Now, since we're on the surface of Earth, the object is accelerating due to the force of gravity. Every object on Earth experiences the force of gravity. It's the force that pulls the block down to the surface of the table. And because of this, there's also another form of energy in play here. Gravitational potential energy. Now, potential energy works a little differently than kinetic energy. It's energy that is stored, ready to be converted into other types of energy. And the farther away an object is from the surface of the Earth, the more gravitational potential energy it has. So, when I hold the block 1 meter above the surface of the Earth, and knowing that its mass is 0.091 kilograms, and the acceleration due to gravity on the surface of Earth is 9.81 meters per second squared, we can record the magnitude of its potential energy as 0.893 joules. And when I drop it, all of its potential energy will transform into kinetic energy. Let's take a look. Did you catch that? Probably not, since energy isn't physically visible. But you could see that the object was accelerating due to gravity. Let's do this again, but this time we record the time it takes for the block to hit the surface of the table. Alright, ready? Go! It'll take the ball approximately 0.45 seconds to fall to the table. Now, using the acceleration due to gravity, which we know to be 9.81 meters per second squared, multiplying that by the time gives us the velocity of the ball before it hit the table. And so we know that the ball had a velocity of 4.4145 meters per second at the instant before it hit the table. Now, using the formula to find kinetic energy, you can see that the ball's potential energy, 0.893 joules, is just about equal to its kinetic energy right after the fall. That's the law of conservation of energy in action. Now, all this talk about energy sure is giving me a lot of energy. I think we should take this outside.
Alright, so I'm back up here with my bike and I'm going to be riding down this hill. And what should happen is that my energy up here should equal my energy down there. Let's go try it out. Oh, let's check the speed on that one. Wow, 21.7 miles per hour. That was fast. Almost too fast. Let's go to the drawing board.
At the top of the hill, I had a certain type of energy called potential energy, which we're going to represent as U sub G.
At the bottom of the hill, I had kinetic energy, which we're going to represent as U sub k. Now, what I want to figure out is the final velocity that I had at the bottom of the hill and see if that matched what our actual value was. Now, to calculate potential energy, we have to use the equation mass times acceleration due to gravity times height. Now, to solve for kinetic energy, we're going to use the equation 1/2 times mass times velocity squared. Now, since our potential energy at the top of the hill was equal to our kinetic energy at the bottom, we can simply set these two equations equal to each other. So that becomes mgh equals 1/2 mv squared. And because there's a mass on both sides, we can just cancel that out. That makes this equation a lot easier. Now, g, we know, is the acceleration due to gravity, which we know to be 9.81 meters per second. And the height of the hill that I was on, from where I started to where it ended, was approximately 10 meters. So we'll use 10 right there. And that's equal to 1/2 times velocity squared. Now we can multiply these two numbers together and multiply both sides by 2 to get rid of that 1/2. And then we get 196.2 equals velocity squared. And we're just going to take the square root of both sides. And using our handy dandy calculator, square root of 196.2, our final velocity is approximately 14 meters per second.
And converted to miles per hour, that's about 31 miles per hour. Yet, the actual velocity recorded outside was only 21.7 miles per hour. Okay, what the heck? Why is the velocity I calculated here not equal to the velocity that I was actually going? Did I break physics? Did I break the law of conservation of energy? No, that's illegal. Energy was indeed conserved, but not all of it was transferred into kinetic energy.
Friction is the resistance that one object or surface encounters when moving over another. When I rub my hands together really quickly, my hands are experiencing friction. It kind of burns, so I'm going to stop now. Burns. Heat. Thermal energy. You see, energy can be converted into thermal energy. It takes kinetic energy for me to rub my hands together, and the more I do it, the hotter and hotter it gets. This is because the kinetic energy of my hands is transferred into thermal energy by friction. The wheels of this bike just so happen to rub against the pavement here. This creates friction between the wheels and the pavement, thus creating thermal energy. Great, now this throws over calculations. Now the potential energy at the top of the hill is not equal to our kinetic energy at the bottom. Instead, our potential energy at the top is equal to the kinetic energy at the bottom and the thermal energy created by the bike.
Friction now affects our equation. Now, our gravitational potential energy doesn't equal our kinetic energy, but instead, our gravitational potential energy equals our kinetic energy plus our thermal energy.
But wait, there's still one type of energy we forgot to account for. Rotational energy. Also known as angular kinetic energy, it is kinetic energy caused by the rotation of an object. Now, remember, there was friction on the hill. If there was no friction at all, the wheels on my bike wouldn't roll at all. They would just slide down like this. However, on a surface with friction, the wheels roll due to the resistance caused by the friction, like this. Now we have to update our equation yet again.
Now, our gravitational potential energy equals our kinetic energy plus our thermal energy plus our rotational energy. And now this makes a lot more sense. Our gravitational potential energy is the same as it always was, yet is being converted into more types of energy, which means our kinetic energy is less than we initially thought it would be, and in turn, our velocity is less than we predicted it would be.
But wait, there's more. There was also wind outside, which affected how fast I moved down the hill. Also, the planet's alignments affected my gravitational energy. The springs and suspension forces in my bike, the air molecules between me and my bike, the electrons and protons between me, my bike, and the road. There's so many factors that it's near impossible to calculate it all exactly. But those tiny factors aren't really what matters. What matters is that we know they exist and we can understand them in the real world. And hey, that's pretty cool.
You can always break the law, but you can never break the laws of physics. And as always, thanks for watching.
Hey, is that my bike?